Okay, so let me share my screen. And this is where we're headed towards. It's a big chapter, actually. We probably won't finish it today. This is chapter 8. Tova, did you get it? Do you have chapter 8? I sent it out.
Yeah, got it last time.
Yeah. Okay. Okay. So let's start. So we're talking. The topic is memory management strategies. So that means, well, sorry, if you could put on your video, I would appreciate it. Um, Memory management is, thank you, is one of the jobs of the operating system, right? I think one of the questions on the midterm was, what are the jobs of the operating system? So one of the jobs is to manage the memory, which means to allocate, to divide the memory up between the different processes that are running. Not all the processes can use all the memory. Each one has to have, first of all, they have to have a limited amount. And secondly, we also don't want to allow one process to use the memory that another process is using while he's using it. That could mess him up. So, like we said, the operating system is like a policeman in the sense that he keeps everybody in their own territory. So you have to divide up memory. Now, the truth is, you actually could know how much memory a process needs when it started up because you loaded, you copy it into memory. So you sort of know how much it needs. Maybe it's going to use some more as it's running, but you kind of know why does it process in memory? Well, you've got arrays in your program and the code of the program itself, the lines of code. If you've got a million lines of code, that's going to be a lot of memory that it's going to be required. When we say memory, we mean the RAM that we talked about. So the RAM is going to get used up by this process running, either because the lines of the actual code have to sit in memory, or because it has variables and arrays and all kinds of data that it's accessing. So that's the need. I've explained now the need for why we need to manage the memory. We need to divide it up. We need to protect one process's memory from another process's memory. So one process shouldn't interrupt the other process. So those are some of the goals here. Um, Let me from current slide. Okay, so this is chapter 8. Um, Background. So when you want to run a program, it has to be brought from the disk into the RAM, into the memory, and placed within a process for it to be run. That's a funny language. What do we mean placed within a process? It means the operating system has to create a running process, and then that program will be that running process. Sort of a funny way of saying it. It's placed within a process. Like it's like the operating system makes an empty process, and then it puts this process in. Okay, main memory and registers are the only storage the CPU can access directly, right? Which, in other words, the CPU is the brain of the computer, which means it's doing all the processing. It's adding things together, and it needs the program to be in main memory, which is the RAM. That's why we need to do the first. Really, these two lines could be switched. In other words, main memory and registers are the only storage, and therefore we need to copy the program into the main memory so the CPU can access it. Because as long as it's on disk, you can't run. You can't run a program from the disk. All right, this is background. Memory unit only sees a stream of addresses. In other words, okay, the memory unit, when we're trying to read memory, it gets one address, another address, fine. Register access in one CPU cycle. That's not so important, but fine. If you want to access a register, which you haven't learned about yet in your other course, but you'll get to, I hope. In the course on computer architecture, there are registers where all the data is manipulated. It takes one clock cycle. Okay, not that important right now. But a main memory access can take many cycles. Okay, these are all things from the other course that you should talk about in architecture, which is that in the computer architecture course, which is that the slowest action that the computer can do is to access the memory. It's a slow action. And we'll talk about that later in the course and later in the slides. Now there's something called cache. Oh, it can cause a stall. what is a stall? Sorry, a stall means that I can't do the next action I'd like to do because I'm still waiting for the memory to be available, right? I asked for some memory and I'd like to do the next command, but I have to wait for the memory to come to be ready. Okay, cache sort of is to solve that problem, which it sits between main memory and the CPU registers. In other words, it's very fast. It's almost as fast as the registers. And you copy some chunks of memory into cache, and then you hope that the chunks you copied are the ones that you're going to need when you do a memory read. So cache, the idea of cache is that the way I would explain it is like this: like if you're running a library, you may have like, or even in your house, let's say in your house, you have a storeroom where you keep lots of your Safari, and in your living room, you only keep some Safari, the ones that you're using constantly. Sometimes you change them though. Sometimes you realize this is a set. You decided you're going to start learning this other set of books. So now you go to your storeroom and you pick a set of books from the storeroom and you put it in your living room library, and you got to take something out of your living room, put it in the storeroom. So why do you do this? Because it's faster to access things in your living room than to every time you want a book, go to the storeroom. But living room is limited in its space. So you can only put some of your most necessary books there, the ones that you use all the time. Ones that you rarely use, when you actually do need them, you have to copy them. You'll have to move them into your living room. So that's the idea of memory and cache. That the parts of the memory that that a particular process is using all the time, he will put into what's called the cache memory. And hopefully, whenever he needs to access memory, he'll find it first in the cache, and he won't have to go down to the basement to the main memory and bring it up into the cache. Now, the cache is hardware, just like the main memory is hardware. It's a kind of RAM, but it's much faster RAM. It's actually called SRAM, very fast RAM, and you copy it there. And actually, yeah, okay. And so that means each process is going to have, some access to the cache. There could be theoretically. Well, this is an interesting question, which is, will you divide the cache up also among the processes, or when a particular process is running, will he get all the cache? Will he get all the space in the cache? Remember, different processes are running at different times. So when a process all of a sudden gets the CPU, does he get to use anything in the cache, or does he get to fill it up with his own stuff, or not? That's an interesting question. Protection of memory required to ensure correct operation. That's what I was talking about. One process shouldn't access the memory of another. Okay, these are background questions. So here's the basic idea of how to differentiate memory by having what's called a pair of base and limit registers. These are registers, which means you put their hardware, you put this number into it. And what does this number mean? Well, this drawing is kind of upside down, but whatever. They put 0 at the top and the high number at the bottom. I would have drawn it backwards, but just understand that. So this is like your memory. This square box is all the memory of the computer. What did you ask? Is this the location? Or I'll explain, and then if you have questions, you can ask. This is all the RAM of your computer. And each process gets its own little section. That's what this means. Process, process, process. Operating system sits in the beginning of the memory, and the end of the memory is, let's say, unused. This blue area is, let's say, unused. So, because maybe it's ready for another process that wants. Now, what is this base and limit register? So the base register means that he starts at 300,040 location in memory, and he goes for an additional 120,900. In other words, the limit is not the ending point, but the size, like how many more bytes. So you add the base and the limit together, and you get 420,940. In other words, that would be you can't access anything beyond that. So why do we have this base and limit register? We put that in hardware. And we say like this, every time this process, let's call this process Harry or P1, let's call him P1. When P1 decides to access something, so he says, he says, I want to access this certain location in memory. We check if the number that he's trying to access is greater than the base and less than the base plus the limit. In other words, it's got to be within the bounds of his memory, what is allocated to him. That's the policeman's job. So every time he does a memory access, he has to do that. So this is going to slow us down because we have to just check every time. That's why we build it in hardware, because anything in hardware will always run faster. So we build a special register, and every time he wants to access, it's going to be this. Now, when the CPU is running this process, this will be the values in the base and limit registers. When process P0 starts running, then the CPU has a job to do. His job is to erase this number and put in the number 256,000 into the base register. And whatever the difference between these two is. Yeah, 44,040. He'll put in the limit register. And then when this process is running, every time he does an access to memory, he'll check the base and limit registers. So as I switch between processes and processes, which we call a context switch, every time I do a context switch, I should change the values in the base and limit registers to reflect the area that process is supposed to be using of memory. Now, only the operating system can change these values. Otherwise, we'd have chaos. If this process could change his limit register, then he could give himself permission to go into the memory of this process. Right? So only he can affect these two registers, only the CPU. We say it's special fast hardware. He must check every memory access to be sure it's between the base and limit. Notice it says in user mode, unless he's doing a system call. Unless the process is running a system call when he's in kernel mode, then he can access any location. Because he's going to actually have to access things in the operating system. Right, that's a side point. The main point is to understand what a base and limit register is. There's a picture here. So the CPU says, I want to he generates an address. It says, please read for me address 1173, I don't know, some number. And we say like this, is the number, let's check. Is it greater than the base, greater than or equal to the base? If no, then we don't let him go on. If you're finished. We have an address error. You can't go there. If it is greater than, then check, is it less than the combination of the base and the limit? In other words, is it beyond the n? If it's less, then everything is great. And we go yes, and we go to get the memory. Otherwise, no. So we have to do two checks. We have to check against the base register and the base and limit register. And the combo of the two. A little bit stupid if you think about it. It should be that we put the base here, and here, and don't even in the limit register, it shouldn't really be this value. It should be 420,940. Should be this value. Then we just check that. Why is it? If we're adding them together, then that's what this means here. Anyway, whatever. Is that clear? Any questions on it? No, you're totally lost. You're not able to ask a question because it's too complicated.
Could you just explain the first part? I get the base plus the limit because that means the end, but what's the first part with just the base?
It has to be greater than the base. If you go back to this picture, I can't access, if I'm process P1 over here, I can't access location 200,000.
Meaning basically the process just has to have started.
The process to what?
Have started.
Not started. No, this is the process is obviously running. He started, but he's been assigned a location. It's like I don't know if I give you another. It's like he's like a country, and this is the border of his country. He can't put his soldiers anywhere outside of this border, which means that The soldier has to be in the area which is demarcated as between the number 300,000 and 420,000. So it has to be, if he tries to put a soldier at a location less than 300,000, then he's putting it in somebody else's country. So that's what this picture means. The address has to be greater than the base. Because if it's less than the base, then he's in the country before him. Okay. All right. This is like oh, okay. This is address binding. This is a term that you may encounter, and it sounds very mystical. Address binding sounds very complicated, and I'll tell you the basic idea. The basic idea is like this. When I write a program, I don't know anything about these numbers, what number, where I'm going to be sitting. Because in fact, when I run the program one time, it might be put me over in this box. And when I run another time, it might put me in some other location. So I don't know anything about it. Yet my program itself must have in it addresses where to go to. You don't think about that, but like, it's really a pity you didn't learn assembly. I was actually just talking to Bonnie, and I think that for next year, I would like you to learn assembly because it's useful to understand how a computer works. But the basic idea is, I mean, not for you guys, for the poor souls that come after you. I don't know. I think it's an easy course, actually, much easier than this.
No, I think we're doing something like that now.
You're doing something like that in assembly, yeah? So did you learn like how do you make a loop in assembly? Did you learn that?
We just started like last class.
Oh, okay, good. So what did you do? Do you remember?
It's like a made up one. It's called Marie. It's from like the text, like it's from like the textbook.
Well, how do you do it? How do you go back in? Let's say you have a loop. If you think about why is it called a loop? It's called a loop. Sorry, you don't see me so well. Why is it called a loop? Because you go down a bunch of lines of code, and then you say, "Oh, my loop isn't over." Go up and go again and go again. So you're actually jumping up. So in assembly, we have a command called jump, which means jump up to the line 10 lines previous. That's a command in assembly. So, so that line, you have to know where it is. If I say jump 10 lines previous, I got to know, is that line 1, 2, 3, 4, 5? Which line is that in my program? So let's say I say it's line 5 in my program. So I write jump to line 5, to memory location 5. But really what I have to say is jump to location 300,045. Because what I think of as 0 is really where I start, which is really just here at 300,040. So there's a discrepancy, there's a difference between like the theoretical addresses that I wrote in my program and the actual addresses that I'm going to be set in. And I never know what the actual addresses are until I'm actually running. You see the problem? In my program, if I'm saying jump to line 5, well, that's going to take me over to here in the operating system. I can't go there. So how am I going to say in my program, jump to line 5? So the answer is somebody's got to change all of my addresses. And that's called address binding. You get to change the address from 5 to 300,045. So that when I jump back, I'll go here and not over here. And not in the actual. So that's the concept called address binding. So here, let's read it. Maybe you'll, if you stop me if you don't understand something. I think it's not so hard. Okay, I said like this. Programs on the disk ready to be brought into memory to execute from an input queue. All right, you don't have to know what this input queue is, but anyway. Remember, a scheduler may have put a process onto the disk. Okay, fine. Without support, must be loaded to address space 0. So that's what he's saying. He's saying, well, one solution would be to put your program in address 0. Don't put it over here. Put it right at the beginning. And then 5 would be 5. But obviously, what's the problem with that?
That address could be taken.
Exactly. There could be some other process there. You can't put every single process over there. What do? Put all your programs in the same place? That can't work. So that would be one. That's what it. So he says here, without support, you'd have to put it at 0. Inconvenient to have the first user process physical address always at 0. But how could it not be? Everybody thinks he's at 0. Every program when he's written, he thinks his first line is 0, second line is 1, etc. Further, address is represented in different. Okay, this is another point. So compiled. So wait. Further, address is represented in different ways at different stages in the program's life. First of all, in the source code, you don't usually write when you write in like C++ or C# or JavaScript or Java or whatever language you learned in a high level language, it's not assembly. You don't write jump to line 6. You write jump to some other line. You write, you don't write jump to a line number. You write go back to where it says for or where it says while. You know what I mean? The parentheses or the braces make you go back to where it says while. You don't know the actual line number. So he says like or jump to count or something. I don't know. He uses a funny example. I would say like the while loop. Compiled code addresses bind to a relocatable address. So compiled code addresses. So once you've compiled it, you're going to actually put it into what's called a relocatable address. In other words, a relative address. For example, 14 bytes from the beginning of the module. Not line number 14, but 14 from the beginning, whatever that beginning may be. Then you have something called a linker or a loader, which will bind the relocatable address to an absolute address, i.e., if you put in this example, he's saying like this: your base address, your base, not your limit, but your base is 74,000. So line 14, it's 14 bytes from the beginning, would be 74,014. And that will be the job of something called a linker or a loader. So in other words, you have a compiled program, but before you can run it, there's something called a linker, which has to assign it a location in the memory and then change all the addresses in your program to reflect your actual location. So all your references to memory location 0 will be 74,000. Will be a reference really to 74,000. All your references to any other location will be that location plus 74,000. So, okay. This is all theoretical ideas. We're going to get to some more practical example, but so basically there are 3 times that you could do this. One would be at compile time, you decide where it's going to sit in memory. And then it would be absolute code. The code would really be written exactly where you're going to jump to. And then when you load it, you'll have to always put it in that place. And that was the original idea. Because that's the problematic way of doing it. That somehow one program will be written at 0, another program, the programmer will have to know, no, I'm not going to be at 0, I'm going to be at some other place. That's like an untenable way of doing it, but that's theoretically possible. That'll be absolute code. Relocatable code would be that the loader will do this job. When he loads it into memory, he'll rewrite your program so that all the addresses will reflect the actual place you are. But in both of the above cases, when the program is actually running, the addresses are the actual physical memory addresses. Now, at runtime, it's already finished. When the program is running, you know exactly where you are in memory. There's another third idea, which is execution time, which is you leave the addresses in their primordial state, in their theoretical state of being like 0 or 1 or 2. And at runtime, every time you jump to a certain place, then you change the address at the runtime, which actually gives you an advantage. Now the process can be moved during execution from one segment to another, from one location to another. But that means every time I want to compute an address, I compute the physical address on the fly. Are you familiar with this expression, on the fly? It's like a general term. It means like while it's running, like as I'm doing it, it's like, while I'm running the program, I may decide to move some part of the program somewhere else, and I'll have to recompute the address every time every physical address. I'll have to compute it as I'm addressing it. This must be fast, going to slow me down. So you need special hardware for this, which is the base and limit registers. Okay, that's just basically, this is checking an address that I have. But I could also get the address and then just add to it the base address, and then I'll get my address that I need. Notice he'll give me an address like 0, and then I'll add to it the base address, and then that'll be the actual address that I need. If my base address is 300,040, then I'll just add to it every time that number. Then I'll know that my number will always be greater than the base address. I won't have to check that it's greater because it'll always be greater because I'm adding the base address to the original number I got. But I will have to check that it's not gone too far, and therefore I'll have to check this. So that would be called dynamic address binding, or execution time address binding. That's actually the way most programs actually run. That's actually the way it's done nowadays. Even though it's the most complicated, that's the idea. That while the program is running, I compute every time there's a memory address, I recompute what the address should be based on what my base address. Based on this register, the base. Okay. All right, now we'll forget that topic and we'll go on to a different topic, which is related a little bit, but different. So right. So we have something called a logical address. Well, first of all, we have something called a physical address space, or address space. What is address space? Address space is the range of addresses that that a program can access. The space in memory that he has. So, for example, a logical address is what's generated by the CPU. In other words, in my program, I say, go to address 10. But that's a virtual address. It's not the real location. The real location that I want to go might be, 300,000 and 50. It's 10. In other words, the physical location is different from what the CPU says. When the CPU reads the program, he thinks go to location 10. But the registers are going to have to change that around to the actual physical location. Logical and physical addresses are the same. So if we're talking about compiled time, then the logical, that's absolute code. So then the actual addresses that I generated at compile time will be the physical addresses. Well, logical and physical addresses are the same in compile time and load time address binding. Logical or virtual and physical addresses will be different if we have execution or address binding, if they in execution time. Here, in other words, if every time I generate an address over here, I add to it the base register, then the logical one will be different from the physical one. Okay, that's obvious. So what is the logical address space? Is the set of all logical addresses generated by a program. What he thinks he's going to. The physical address space is the physical addresses generated by a program. It knows all the places that he actually will go to. For example, if your program has a line like this, loads some data from location 100. In runtime, this will be changed from 100 to some other number. Obviously, if this conversion is slow, your program will be slow, and that's why we had our. That's kind of repeat. Actually, this actually repeats kind of what we said. We're still we're still getting to introduction. I'm gonna skip that. Okay, so there's a memory management unit called the MMU, which is a hardware device that at runtime maps the virtual address to the physical address. So if we're going to talk about change, I mean, basically, I already said it over here. We need to add the base register to the CPU address. So here's a new picture. And here we go. The logical address the CPU comes up with is 346. Go to line 346. This is the base register, which we're now going to call the relocation register, but it's essentially the base register. We give it a new name. And we're going to add it, and the MMU will create this address, and then we'll go to the actual location. I mean, that's what I explained already. The point is that the program, if 4 different people write 4 different programs, and they all say start at memory location 0, and now and jump to line 10, and then jump to line 5, they can't all be located in physical place 0 because they can't run at the same time in then, because they'd be overlapping each other. So we relocate them based on our relocation register, and then we generate the actual address like that. And that's the job of the MMU, and it's special hardware that's very fast. So here you see the base register is now called the relocation register. The program never knows about the physical addresses. It's the job of the MMU not to be confused with MMY. You guys know what MMY is? It's a seminary in Baca. It's a girls' school. But this is the MMU. And the MMU is, like I said, is this thing here, which does this calculation. Okay. I think I'm going to skip dynamic linking. I'm going to skip this. But swapping we have to talk about. Yeah, I'll just say one thing about linking. Linking is basically this idea. When you say include in your program, did you ever write include at the top of your program? Anybody? You ever write an include? You don't do that in C# or anything?
No, we use using. Is that the same thing?
Yeah, using. Okay, there you go. Thank you. Using. You say using, and then you're using what's called a library, a system library, some library of other functions that you didn't write, right? If you want to use a program, a function that you didn't write, you say using. Is that what it is? I don't remember. I'm more of a C++ person. But in any case, you say in other languages you say include, which means I want to use this function that I didn't write, but I need to include it in my program. So that means that it's not just like I write these words, then magically I can use it. When the compiler compiles my program, it joins into my program other code that was written by that other person so that I can use his functions. That's called linking. Okay. Swapping. We're getting there. We're getting there. Okay. Swapping. Here, let's just see. The picture is easier than the words. What do we see here? We see here's the operating system. This is the main memory. This is the actual memory. And what we can do is like this. If we want to put all of our programs in our main memory, so we'll do that. We'll put this process in memory and this process in memory. So we could probably put 2 processes in memory if they're this size. At a certain point, though, I want to put another process. At a certain point, my memory is full and I can't put another process into memory. So what we do is we swap out one process. We choose what we call a victim. Some process is going to be the victim. We remove him from memory and we put a different process in memory so that he can run. Now this process is on disk. When it says backing storage, it means the disk, a hard drive. This guy's on disk, he can't be run until he's swapped back in. And I have no choice because I have a finite amount of memory, really. I mean, I also have a finite amount of backing of disk, but it's much bigger. So I put him out. That's the idea of swapping. So here we saw swapped, backing store, that's the hard drive. Roll in and roll out. That means put somebody out and bring somebody in. Major part of swap time is transfer time. Total transfer time is directly proportional to the amount of memory swapped. Right. Obviously, if I'm gonna put a bigger process onto the disk, it's gonna take more time, depending on how much data it has. So the ready queue we already talked about, actually, which is those people that are in memory, that are actually over here and are over here in the main memory and are waiting to get the CPU. These guys are really not in the ready queue. They're not ready because they have to go through a certain procedure before they can become ready. And then what's that procedure called? Swap in. First, we have to copy him. Then he'll be ready. Okay. Does the swap out process need to swap back into the same physical address? Oh, you hear the question? Let's say I swap somebody out and now I swap him back in. Can I put him in a different location? What do you say? It depends on what? Put it that way. It depends. Depends on what we just said, what we just learned. This is like a review question. What if the address binding is absolute code, created absolute code, versus the address binding is dynamically, is on the fly with the MMU?
If it's dynamic, we'd probably need to get back to the same, no?
No, reverse. But thank you for attempting. but the reverse. If it's dynamic and the memory computations I'm doing on the fly as the program is running, then it doesn't matter where I put it. I'll just change the value in this relocation register if I put it to a different location. And every time I do a memory access, I'll just have a different value here now because I put it in a different place. But if it was absolute code, we refer to as absolute code over here, where I actually generated the addresses at the compile time and it's fixed permanently, then I'm going to be in this kind of picture. And it has to be, I take whatever the CPU gave me and it has to be valid. And if I put it in a different place, it's not going to work. And that would also be true for load time. Because once I loaded it, I only load it once in the beginning. And then I fix its code wherever I fix the address. Swapping would have to be, I wouldn't have an MMU. I only have the MMU in what I call dynamic. What does he call it? He calls it execution time binding. Fine. I would say this is a great question on a date. You can ask somebody. Do you prefer do your programs use execution time address binding or load compile time address binding?
I'll be sure to ask him.
Yeah, ask your next date if what he thinks about that. That'll really surprise him. Anyway, so where we're here he calls dynamic loading, right? I called it dynamic loading, but here he called it whatever, different names for it. Called it what did he call it? Execution time. Execution is the same as dynamic. Okay. That's dynamic linking. Okay, so the swapping we were talking about. So does the swapped out process need to swap back into the same physical address? And we answered it depends. If it's using the MMU, then no. But if it's not using the MMU, then it's fixed and it has to go back to the same place. That's what it says here. Depends on the address binding method. Plus consider pending IO to and from process memory space. Right, what if there was some IO thing and I swapped him out and some data was supposed to be read from the keyboard and I swapped him out and now finally the data is ready and I swap him back in and he's in a different location. The IO has to know where to give where the program is. So that's going to make things more complicated. Right. So in reality, it used to be, I would say, in the 90s and 2000s that there was swapping was done. But since the 2010s, this is my feeling. I don't really know this for sure. We don't really do much swapping anymore because our memory is large enough. Our memory is usually so big that we don't really need to do swapping. And swapping is very, it slows everything down. But there was a time when we did more swapping. So what it says here is, sorry, where were we? In Unix, Linux, and Windows, swapping is normally disabled. We don't do swapping. And we only do swapping if we're running low on memory. That's the basic idea. Okay. All right, we've been talking about context switching a lot, and now let's talk about the time of context switching, right? What can somebody tell me what context switching is? This is an important concept.
The time it takes between two processes to switch, like with the CPU.
Yes, yes. But the context switch is not the time. The context switch is the switching, and now we're talking about the time. How long does it take? But the context switch itself is the switching between one process, when the CPU stops working on one process and now starts working on another process, or the other process gets the CPU. Exactly, perfect. If the next process can be put into CPU, if next process to be put on the CPU is not in memory, then we need to swap, assuming the CPU is not completely idle, not doing any, if he's doing nothing, well, maybe. We need to swap out a process from the CPU and swap into the target process. So that is, if a program wants to be run and he's not in CPU, we need to swap somebody out and put him in. Basically, the CPU, I guess you could say, always has somebody in the CPU because it could be the operating system. Unless, I mean, I guess unless the operating system went to I/O or something, is waiting for some event, I guess theoretically the CPU could be completely unused. But in general, somebody's there. We want to bring somebody in. We need to swap that guy out. This is different from swapping here, and we're going to use these terms to clarify in your head. Swapping always refers to putting it to the disk. When we're talking about taking it from memory into CPU, we're always going to use the word switching. Even though in English, switching and swapping mean the same thing, but swapping always means to disk, and switching means switching between the CPU. The CPU, who gets the CPU? I guess the swapping sounds like it's a little bit slower. Switching is very fast. And so that makes sense because the CPU is fast. Context switch time can be very high. Can then be very high. For example, if I have, see, here's the kind of question you could ask on an exam, because it's math. I mean, you can also ask, I could ask any of these things that we talked about. What is the advantage of execution time binding using the MMU? What is the advantage? Anyway, but here, if we have, let's say, 100 megabyte process, and we need to swap him, oh, this is confusing, because here it talks about switching, and now we're talking about swapping. But notice it says swapping to hard drive. If you have a 100 megabyte process, we want to swap him to the hard drive with a transfer rate of 50 megabytes per second. Well, 50 megabytes, that means this is going to take at least 2 seconds, right? Because 100 megabytes at 50 megabytes per second is going to take me 2 seconds. Everyone sees that? I'm just basic. I'm going slow here. I just want to get some thumbs up here. 100 megabytes, if I want to copy it from memory to the hard drive, and I have a rate of 50 megabytes a second, then it's going to take me 2 seconds. So that's what he says here. Swap out time is 2,000 milliseconds. And remember, I want you to know that a millisecond is a thousandth of a second. So 2 2,000 thousandths of a second is 2 seconds. Right? I want you to know 4 things for your whole life. A byte is how many bits?
8.
Thank you. Great. A millisecond is a thousandth of a second. A microsecond is a millionth of a second. A nanosecond is a billionth of a second. And then I also want you to know that a megabyte or a kilobyte, let's say, is 2 to the 10th bytes. A megabyte is 2 to the 20th bytes. And a gigabyte is 2 to the 30th bytes. This goes 10, 20, 30. Kilo, mega, giga. 2 to the 30th. And the 4th thing you have to know is that every digit of hexadecimal is how many bits?
4.
Oh, Ariel, you get the salash today. You're answering all my questions perfectly. Thank you. Exactly. Those are, I say that in a few of my classes. Those are like sort of, that's like the times tables of computer programming. You know, you got to know what 2 times 2 is. You can't really do much math without 2 times 2. You got to know what 4 times 4 is, 4 times 5 is. So you got to know these things. Okay. So again, so he just, to confuse you here he wrote seconds and here he wrote milliseconds, but we know that milliseconds are thousandths of seconds, so 2,000 thousandths of a second is obviously 2 seconds. Plus, swap in the same size process. Oh, if the new process is also 100 megabytes, then all of a sudden we're talking about 4 seconds. That's a ton of time. For a computer, 4 seconds is a ton of time. We want things to happen in nanoseconds, not in seconds. The total. Wait, you know, I should fix this slide. Oh, it's a little bit annoying because here he's talking about swapping, and here he's talking about context switching in the CPU. Because he's imagining like this. I want to do a swap. I want to do a context switch, but oy vavoy, the program that I want a context switch is on disk. So it's going to take me even longer now. I'm going to have to swap him in and swap somebody out and then do the context switch. So it's a little bit confusing example here because he's combining context switching with swapping. So the total context switch swapping component time of 4 seconds, right? Very just how do you read this sentence? We're talking about the context switch has a component which is called the swapping component. That's going to be 4 seconds. And as you can see, since it's 4 seconds, that's too much time. That's why modern operating systems don't even bother doing this swapping. They don't use the disk for storing programs. Hopefully they have enough memory to keep all the programs in memory. You can reduce the size of memory swap by knowing how much memory really being used, right? Theoretically, you could just swap in, not the whole program, but just part of the program. You don't have to know this request memory. Other constraints as well on swapping. Pending IO can't swap out, as IO would occur to the wrong process. In other words, the poor, unfortunate IO controller has no idea that his process got swapped out, and he'll just give the results of whatever the guy typed on the keyboard to the wrong process. So if the process is waiting for the keyboard, then we can't really swap him out. Unless we put it to some kind of buffer, unless the IO controller puts it in a buffer, and then the operating system checks, knows which process is which buffer, and that's called double buffering. But this also is more complicated and slows things down. So that's what I say here. Standard swapping not used in modern operating systems. Okay, but some kind of modified version is. This is just to point out the problem of context switching. It'll slow down of swapping. It'll slow down my context switching too much. It can cause problems with IO. Therefore, we just don't do it anymore. Okay, now we're onto a totally different topic. This was just about, but this is like important stuff. Let's review. We talked about swapping. We talked about address binding and how the logical address and the physical address are different. We talked about how each process is in a different location, has a base and limit register. The limit is not the end, but is the total size of the area. Okay, now we go on. What is our time? Yeah, let's go on to the next topic, which is memory allocation, which is basically like this. It's related. It's all in the same chapter, so everything's all related, but it's a different topic. Basically, its question is like this. With this process, this memory that we assign to this process, we can describe it with one word: contiguous. What does the word contiguous mean? You probably heard the word contiguous in the contiguous 48 states, right? In the United States has the contiguous states.
Is it
as
not
opposed
repeating or like a unique? Each thing is unique.
No. All the states in the Union are unique. What are the 48 contiguous
All
states?
together?
Yes, they're all together. They're all touching, they're all in one area. Alaska and Hawaii are not contiguous to the rest of the states. Canada is in between Alaska and the rest of the states. And the Pacific Ocean is between Hawaii and the rest of the states. But the other states are all contiguous. They're not all touching each other. I mean, Texas is not touching New Jersey, but they're all in the same, they're all touching somebody who's touching the other. So they're all adjacent. There's nobody in the middle. If there'd be like, France in the middle between the East and the West Coast, then the states would no longer be contiguous. I mean, assuming France would extend from Mexico to Canada. So this memory is contiguous. What do I mean by that? This is process. Oh, where's my here? This first process called process 0. All of his memory is in this region. None of his memory is somewhere else. We're going to see that that's not always the case. That's one idea. That's one design of how to do an operating system. Give everybody his memory in one location. Before I go on, what are the advantages and disadvantages of having the memory in a contiguous location? This is a question for you to think about. What would be the advantages and disadvantages? I'm just trying to get you to, not me just talking the whole time. Yeah, Sarah, go for it.
Maybe if something happens to that location, then all your memory's in jeopardy.
Okay, right. The memory could get corrupted and then you lost everything. We don't think about that. That's a possibility, but that's not really a problem that we usually think about, because if part of your memory gets corrupted, then you're probably your life is ruined anyway. Your program's life is ruined. And secondly, probably but you're right. Yeah, it could be. If this area gets corrupted, then I lost the whole process. But that's not so bad. I'll just restart. Remember, the program is on the disk. The disk, we're worried about corruption. We're not so much worried about memory corruption. But yeah, okay, that could be. But by the way, you could also have corruption if it's spread out. You're saying if the corruption happened in one location. Fine. Okay, I'll accept that. Any other ideas? Why else? What's advantages? What are the advantages of having it all together as opposed to spread out? What's the problem if it's all spread out?
It increases like the time
The time for what?
for like either context switches or like processing things. Like it doesn't have to travel. It just goes from one thing to the next.
Right, just goes from one to the next. Okay, you're right. Yes, definitely. That is definitely an advantage. It's faster. Faster to access memory. We know exactly where we're going. Think about this. You're going to the zoo. And you have a lot of children, and do you want to keep all your children together, or do you want to let them all run around the zoo wherever they want to go? If you do let them go all around the zoo running, what would you have to do? Like, let's say all of a sudden you need to talk to one of them.
keep
You'd
track
have
of
to
all
like
of it.
make communication between them.
Yeah, you'd have to keep track of all of them. You'd have to know where they are at any moment. Let's say if I need to be able to access them all at any moment, I need to keep track of them. So I'm gonna have some kind of overhead to figure out where they all are. Some kind of mapping. I'll call it mapping. I'll have to have some kind of table that tells me where every part of the memory is located. In this one, I don't. I just need to know the beginning and the end that I'm done. If it's spread out, I need to have. So this has an advantage that I don't need to map where all the memory locations are. What's the disadvantage? That's the advantage of it. What's the disadvantage of this? Well, in this picture, it looks very nice. This one is here, this one is here, and this one is here. But it doesn't have to look that way. It could be, for example, imagine like this. Imagine that this process 0, is running, and process 2 and process 1 and 2 are running. 0, 1, and 2 are running. Now 1 finishes. So now what do I have? I have a space here, I have a gap here between 300,040 and 420,940. That's a gap of approximately, of 120,000. And then I have another gap here from 88. How much is this gap? This gap is 880. It's about 140, right? 140,000 bytes. Something like 100,000, right? If my math serves me right, it's 144. Sorry, what is it? 144,000 is the difference. So this is 100. I have a gap here of 144,000. I have a gap here of 140,000. If this process finishes, I have a gap of 120,000. What if I have a process that all of a sudden comes in and says, hi, I would like to be put in memory, and I need a space of 150,000. Can I put it here? Absolutely not. Not enough space. Can I put it here? Also not. This is only 144,000. He says it's 150,000. I can't put him here. That's not very frustrating. I can't put him in, but I have the memory. I have empty spaces. I have a space here, and I have a space here. Together, if they would be contiguous, I could put him in. But if I'm saying that I need to put him in one spot and one spot only, then I can't put him in memory. And yet I have the space. We have a word for this. We call this fragmentation, or more specifically, we call it external fragmentation. It's a term you also have to know. We call this fragmentation. Fragmentation in general means, well, let's say external. Let's talk about external fragmentation, which is this kind of fragmentation. What it means is that I have the memory, but I can't use it because the pieces of memory that I have are too small to be used. It's like I cut, the child came in with the bread, and he has slices of bread, and he cut it into tiny little pieces. He cut all the slices into tiny little pieces. And now I can't really make a good peanut butter and jelly sandwich because I have these like little tiny crumbs of bread. They're fragmented. If they bid whole pieces, then I could have made a good peanut butter and jelly sandwich, but I can't now. So that's called fragmentation. You understand the definition here? That I have the space in memory, but I can't use it because the size of each piece is too small to give me the ability to contiguously allocate the memory needs that I have. Questions, comments? Everyone got the idea of fragmentation? So that's the problem with contiguous. The advantage is I know where all my children are. The disadvantage is, imagine I'm driving to the zoo and I have 7 kids and I only have 4 places in my car. So I can't keep them together. So if I say I'm only traveling to the zoo if I keep my kids together, then I have to rent a minivan. And I may not have a minivan. So The advantage is that I have all my kids together. The disadvantage is I can't use smaller cars. I can't use smaller memory spaces. So let's talk about contiguous allocation. So basically what we've said before up to now is contiguous allocation. What we've thought of up to now. We'll see a solution for non-contiguous allocation. Each process contained in a single contiguous selection of memory. Okay. Relocation register. Where's the relocation register? Which unit uses that? Not the MMY, but the
MMU.
MMU. Thank you. The MMU. The MMU uses the relocation register, which is really just another fancy word for the base register. Used to protect user processes from each other from changing operating system code. Okay. Base register contains the value of the smallest physical address. Limit is the largest offset, how far I can go from there. A little bit confusing. You might think the limit is the end, but the limit is not the end. Limit is how far from the beginning I can go. Each logical address must be less than each logical address must be less than the limit register. Each physical address must be less than the limit register plus the base register. The MMU, here we are, maps logical. This is everything we just said. This is a review. Oh. On context switch, that's supposed to be context switch. On context switch, the new base register is loaded by the scheduler into the MMU, right? Because the MMU will only have the base register for whichever process is currently using CPU, and it'll change when that process changes. So the scheduler has to change, or somebody in the operating system has to change the values in the MMU. This protects processes from each other. This allows the operating system to use more memory or less when needed. Because I could theoretically change my limit register and then give myself more memory. When would I need to do that? If I do what's called in programming dynamic memory allocation. In C++, we use the new command. I don't know what you guys must have done something like this where you dynamically allocate an array. Did you do that?
Yeah, that's also new.
It's also new. In what language? What language? In C#?
Sharp. What? It's
Yeah.
not. Suri's telling me it's not.
No, it's not.
I'm
Yeah.
not sure. Maybe it is. I don't know.
No, like when you create a new object of anything, so even if it's an array.
No. That's
new
yeah.
int
Okay.
or-
Yes. No, you're 100% right, Ariel. I was thinking, yes, when you create a new object as the program is running, right? You have a loop and you make a linked list. And you point there, and then you make another one. That's called dynamic memory allocation. You're creating a new object while the program is running. Now, there's no way that the operating system knew how many you were going to make. You might have a program that has a loop to 1,000,000. You create 1,000,000 objects in your linked list. So you didn't have enough memory when you first loaded into memory. So the operating system has to all of a sudden change your limit register to give you more space. It's going to be a problem if the next process is right next to you. Anyway, nobody does contiguous. Contiguous is just a theoretical idea, used to be done. Nobody does it anymore because of this problem. How are you going to give yourself an unlimited future use? You'd have to, you can't just move the limit register. But theoretically, you could. Okay. This also allows the operating system to use more or less memory when needed. Like we said, kernel code can then be what is called transient, not always resident. Okay, whatever. So this is the same picture that we saw before. But basically, that was the way it worked for contiguous. That was what we saw before. And here we have contiguous. We're basically only explaining contiguous in order to get the basic ideas out and in order to show what the problem with it is. Wait a second. And why we have to go to a different system. Wait, I can get rid of this thing. Here. Okay. So what do we have here? We start off here. I guess I should read this. Multiple partition allocation, each like one or more partitions. This is called we call this a partition. Process 5 is in a partition. Process 2, Process 8, each process is contiguous in its own space. There are fixed size partitioned. We could have fixed size, in which case every process has exactly the same amount as every other process. Of course, that's very inefficient. There might be one process that only needs a small space and one process needs a big space. So we can have variable size partitions. It's because otherwise what? Everybody's gonna have to have only fit their whole program into the same size as everybody else. That doesn't make sense. So we're gonna have variable sizes. So process 8 can be much bigger now. Now what we're gonna have is this is I explained to you already when I talked about fragmentation. This is the fragment. We're now explaining fragmentation. If 8 leaves memory, if 8 finishes, so now we have this big gap, and we can put 9 in there, we can put 10 in there, and we may have a little small space here, and maybe nobody could use it. It's too small. Also, what if 9 finishes now? Now we'll have a space over here and a space over here, and we'll have our fragmentation problem. So we have a hole. Again, hole, block of available memory, hole of various sizes are scattered throughout memory, right? As processes go in and out of existence, right? Processes come into existence, go out of existence. We're gonna end up with lots of these holes all over the place. When a process arrives, it is allocated memory from a hole that is large enough to accommodate it. Process exiting frees its partition. Adjacent free partitions are combined. So if like 10 would go out of existence, then I'd have a hole. I'd have only one hole here, which would be the combined of this gap plus what 10 used to occupy. The operating system will have to maintain information about which sections are allocated and which sections are not allocated. Free partitions, allocated partitions, and free or available partitions. Okay, that's the basic concept. Let's go on. So now we have an interesting theoretical question. Just like this. If I have a picture, pictures are always the better thing to look at. No, I don't have a picture. Okay. Well, let's go back to this picture. I mean, imagine that I have lots of holes here. And I have some that are bigger and some that are smaller. Comes along a new process. Which hole should I give it? Well, there are 3 choices. I could give it the one that, in other words, for example, let's say the process, let's say this space is, let's say 1,000 bytes long, and he only needs 900 bytes. So I'll stick him here, and then what will I have? I'll have a hole of 100 bytes, right? It was 1,000 bytes, and he came along and he said, please give me a space, and I give him this space, and I have a gap now of 100 bytes. And if another program comes along and says, oh, I need 100 bytes, I'll put him there. But, well, if I only have one hole, that's what I'm going to have to do. But what if I have 2 holes? What if I have a hole that's 1,000 bytes here, and another hole that's 2,000 bytes? And it comes along a process and says, hi, I'm 1,000 bytes long. Which hole should I give it?
The one that's 1,000.
Why should I give it the one that's 1,000?
Because you want to fill up, if it fits into the smallest, then you want to fill that up, because if you have a process that's bigger than 1,000 bytes come along next, then you're not going to have any place to put it.
Okay, very good, correct. Can somebody give me the opposite logic? Why would I put it in the 2,000 one? Is there any possible logic to that?
Yeah, because it's more likely that you're gonna have a process that's gonna be between like 1,000, 2,000, than like 100.
Right. Say, yeah. In other words, so if I put it, what's going to happen if I put it in the 2,000 place? I'm going to have a gap of left over there 1,000. Plus, I'll have my original gap of 1,000. I'll have 2 gaps of 100,000, and it's very likely that those will be useful gaps, because the likelihood is that another program will come along, and 1,000 is useful for him. If I put it in the smaller space, which is a close fit, I'll end up with a tiny sliver of memory which almost nobody could use. and I'll have more fragmentation. So now I'm not saying Ariella was wrong. I'm just saying they're different.
Wait, wasn't the program 1,000 bytes?
Yes.
So then it would fit exactly. Why would you have
No,
a
no, no, no. It wasn't 1,000 bytes. Sorry, it was 900 bytes. Did I say it that?
Yeah,
Oh, did
you
I
said
say it wrong?
1,000.
Oh, I said it. Maybe I misled you. Let's imagine that it's 900 bytes, and that I have a one gap of 1,000 and one gap of 2,000. That's what I meant to say. So where do I put the 900? So I thought what you were saying was put the 900 in the 1,000 one, and I'll only have a waste of 100. And then if some other program comes along that needs 2,000, I'll have a space for him. Why ruin the good, nice, big space of 2,000 by putting the 900 guy in there, and I will only have 1,100 left over. A guy comes along 2,000, I won't be able to use it. That's correct. But it's also correct to say, put him in the 1,000 one and leave the. Sorry, that's what you were saying. Put him in the 1,000 one. But it's also correct to say the other way. No, put him in the 2,000 one, and then I'll have a leftover of one. I really should have a picture. Let me draw. Where is this? See why I don't draw. It's hard to draw with your finger on a mouse. But let's say here, I have this, and all right. This is occupied, okay, by some process. And this is, let's say, 1,000. And this is, let's say, 3,000. Let's say it's 3,000 because it looks a little bigger. I'll make it 3,000. 1, 2, here, 3,000. And then comes along this program who needs 900. So if I put him in here, I'll have this little sliver left over of unused space. I have a hole. We'll call that a hole. If I put him over here, let's say I put him at the, let's say I put him, oh. You all see, wait, can you see what I'm drawing? Yeah, okay. Yeah. If I put him here, then let's say I put him here. Put him here. I could also put him here. Okay. If I put him here, I'll have this little sliver of 100. If I put him here, I'll have a bigger area of 2010. Or 2,100. Which is a better place to put it? On the one hand, I might say put him here. That we call best fit. Allocate the smallest hole that is big enough. Now I'm going to have to search the entire list to find the best fit. Unless the list is ordered by size somehow. Now this will have the advantage, this will create advantage or disadvantage to your decision. Produces the smallest leftover hole, a very small sliver. If I put it in the worst fit, let's say this is the worst fit, then I'll have to also search the entire list, put in the largest hole, produces the largest leftover hole. Now I have to decide, do I want the smallest leftover hole or biggest or the largest? Both could be useful, but there's a logic to each of them. The logic of having the largest leftover hole is that it's more likely to be usable by some other process. Some other process is going to come along. Who's going to ever need this 100? Nobody. It's too small. On the other hand, this may be wasted space. In other words, if I put in the largest one, maybe I'll never end up using this. This 1,000 one was maybe such a close fit. I'll just throw away this sliver. Who cares about that sliver? As long as I keep my, now all of a sudden somebody comes along and needs 2,500 and I can't put him here because I used to have 3,000. I could have put him here. 2,500. I can't put him here now. So I should have put this guy over here and had this thing left over. So there's an advantage and a disadvantage to best fit and worst fit. Therefore, first fit and best fit are better than worst fit in terms of speed and storage. So actually, worst fit, even though it sounds like a great idea, is not really such a great idea. Because that guy 2,500 is going to come along. We don't. So we really do put it in either best fit and leave these little tiny fragments, which are going to cause a lot of fragmentation. Or we do another idea, which is called first fit, which will save us time. It's the fastest method. Why is it fastest? I don't have to search the entire list. The first guy that I can put him in, I put him in. And it's kind of a compromise because the first guy that I put him in will either be, he might be sometimes the worst fit. He might be sometimes the best fit. He might be sometimes a medium fit. In other words, I'm going to sometimes create very small slivers if I put him in the first fit. And sometimes can create big areas that I leave off when I put him in the first fit. So it's sort of like an average. So it comes out that really first fit is the best method. You see why? Because there's arguments to say that best fit and worst fit are both advantageous. And actually, first fit gives me sometimes best fit and sometimes worst fit and sometimes medium fit. But it is going to lead to more fragmentation. I mean, worst fit, in a sense, avoids the fragmentation. So we're going to have this fragmentation, all these little slivers. And because what could happen? Like, I mean, whatever, the slivers can get, sometimes they don't go away.
Yeah, but isn't this very short term like storage? So if like the process leaves, then it should be then like you shouldn't have that fragmentation anymore.
Yes, you're 100% right. 100% right. This is a short-term problem. In fact, if your computer memory is fragmented, you just turn off the computer and turn it on again, and it'll be all clear. Or stop some processes. The real problem with fragmentation is on the disk. Sometimes disk allocation can be fragmented, and then it's permanent. And then you have to something called defragging your disk drive. Okay, just to understand these ideas of best fit and worst fit. In other words, I could give you a question, using the best fit allocation, where would I, given this memory setup, where would I put this program? It's pretty simple. Okay. And here we're talking about internal fragmentation, external fragmentation. We already mentioned. The external fragmentation is what we talked about. Total memory space does exist to satisfy the request, but it's not contiguous, and therefore it's useless. Internal fragmentation is when I say, like, for convenience, a larger memory partition than the process needs may be nevertheless allocated to it. This waste of memory is internal to a partition. In other words, I could, a process comes along, and logically I should only give him, I don't know, 10 megabytes. I give him 11 megabytes anyway. But for my own reasons. That would be called internal fragmentation. He doesn't need it, but it's internal to the software. It's internal to the process. The process has it. It's fragmentation in the sense that inside the process, he's got a fragment that he's not using. As opposed to external, it's external from the process. It's between processes, there's some fragments. So what we were talking about up to now is external fragmentation. There's also something called internal fragmentation. Now it says first fit analysis reveals given n blocks allocated, 1/2 of n blocks are lost to fragmentation. 50% rule. In other words, up to about a third, or in other words, what does it mean given n blocks? I think he means like when we talk about memory, we can sometimes refer to it as blocks of memory. So we may say we can describe the computer's RAM memory as being 16 gigabytes. We can also describe it as being 10,000 blocks, where each block is a certain size. So what this is saying is that if you use first fit and you have 10,000 blocks of memory, you're going to lose 5,000 blocks to fragmentation eventually. Even though you can reclaim fragments, This all the time process being created and going out and in and out. You're going to get a lot of fragmentation, and you're going to have half of your memory is going to be unusable because of fragmentation until you restart your computer. That's what this is saying. This is when it says first fit analysis. What it's saying is they analyzed real case, real computers. They checked them, and they found that if you use the first fit, you're going to have a lot of memory loss to fragmentation. You have all these slivers that are useless. Even if you use first fit, which theoretically should be the best way to do it. So that's really bad. We don't want to lose all of our memory to this problem. What could be solutions? One solution could be compaction. Compaction basically means stop everything, have the operating system look at all the processes and move them around and try to make all the fragments, combine them together. Combine all the fragments, get them all adjacent to each other. That's going to mean moving all my processes around. It's going to be a time-consuming process. Shuffle memory contents to place all three memory together in one large block. Now, stick everything down, stick all the programs, since half of it is already wasted, start moving the process down to one section of the memory, and the other section is start to free up. Compaction is possible only if relocation is dynamic. You can't obviously do compaction if you have address binding at compile time. If the addresses are bound to the physical addresses, only if you have dynamic address on the fly address creation, then you could do compaction, because then you can move people around. If done at compile time, we cannot relocate memory. Another solution would be to allow a process memory to be non-contiguous. So the other obvious thing, and the direction that we're obviously headed to, is to say, well, let's give up on this idea of contiguous, and let's scatter it throughout the memory. I wrote here, consider that the backing store has the same fragmentation, right? The hard drive has the same problem, but we're not talking about the hard drive right now. We're talking about memory. And what we're going to say is like this: the memory could be non-contiguous. Now we won't have this problem. We can use tiny little pieces wherever they are. Or we're going to do something different, which is we're going to, well, yeah, we can have, all right, let me take a break here before we talk about non-contiguous memory. Let's take a break. And I'm going to finish anyway. So we'll take like a 7-minute break till by my clock, 7 minutes would bring us to 25 minutes before 6. Resume recording. Okay, so one idea is to divide your program into segments. And actually, this is one system that's actually used very much today. Used in Windows, I think. Well, it's used in the Pentium architecture, in the PC architecture. Segmentation. What does it mean? It means that instead of trying to, basically, I say it in very simplest terms, instead of trying to find one contiguous space for your whole program, we'll divide your program into parts, and each part will be in a contiguous location. We'll divide your program into parts. That's the basic idea of segmentation. We'll say, we'll take your program and we'll cut it up into segments, and each segment will be contiguous. So that will give us smaller pieces, and therefore we'll be able to use those, we'll be able to use smaller spaces on the computer, and there'll be theoretically less fragmentation. Are you guys, is my connection okay? Yeah. Okay. Wait, let me open the door here. Okay. So how do we divide up the program? we divide it up into the main program, like the main, then each function maybe. I don't know why it says procedure, function, method. I mean, they're all the same thing. We divide it into the method, each method or function, whatever you want to call it. We put it in its own area. All the local variables we put in one area, all the global variables in another area. We have a stack. I talked a little bit at one time about what the stack is, but stack is where all data for function calls is stored. Symbol table, we don't have to know what that is. Arrays, all the different parts of the program, we'll call them each one a unit, and we'll put them in different locations in the computer, in the memory of the computer. So a user's view of the program, right? My program has all of its subroutines or its functions. It has a symbol table is like a list of like the names of the variables. The main program, maybe what is SQRT? That's like a library function, square root. Library functions, these are my functions, library functions, the stack, the main program, or these are all the different parts of the program. And what we do is we take those different parts, 1, 2, 3, and 4, and we put them in different locations. Now, the segments, if you notice, are not all the same size, but they can be scattered throughout the computer. So basically, I'm just saying the program is no longer contiguous, and therefore it'll be easier for me to find a place to put it because it's cut up into pieces. That's the basic idea. How do we locate these? We're going to have a mapping, some kind of mapping thing where we have a segment number, and then notice where the segment is. First of all, its number and where it is, or really, it's really the where it is in memory, and the offset within it. For example, I need to know that say 2 is located here, and then if I need a particular line in 2, that's the offset. How far within 2 to go to get what particular thing I need. So we have what's called a segment table, which is our mapping. It maps a two-dimensional physical address. It maps two-dimensional physical addresses. Each table entry has a base and a limit. In other words, where the segment starts and how big the segment is. And then if I give it if I know I'm in segment for the memory, I know I'm in segment 6, so I go to that location and then I can go find it. The segment table base, so there's a register for the segment table's beginning and its size. And again, I'm going to check that any address is legal if it's greater than this segment section. But notice that I'm going to have for each segment, I'm going to have a base and limit register, because I don't know how big they are. And I got to make sure, right, you're not going to memory that you're not allowed to go to. Okay. We'll also put a valid bit for each segment to say whether it's in use at all or not. It might be, for example, that your program has no functions. So the function section might be invalid, not in use. Protection bits associated with code sharing occurs at segment level. What do I mean by that? They mean that it's potentially possible that 2 programs could have segments that overlap. In other words, this is one program. There's another program that's sitting here in this gray area, let's say. Well, his segment could actually overlap this one if he's sharing a function. That's not important, but that's a possibility. Okay, so here's how this is basically the same thing as the contiguous, but for each segment, we're going to do this. We have to have special hardware. The computer is going to give us an address, right? The computer says, go to address SD. We're just dividing the address into 2 parts. In other words, the address is really just ones and zeros. It's, let's say, a 32-bit architecture. which means you have a 32-bit address length. And we'll divide it. We'll say the first 16 bits or the first 10 bits, many possibilities. But let's say the first 16 bits are, from the CPU's point of view, it's just an address, just ones and zeros. But really, there's a meaning, a special meaning to it. The first 16 bits tells me which segment it is. So I go to the segment table, and the amount, if this number is, let's say, 15, then I go down 15 rows. That's why there's like a brace here. That means how many rows to go down based on this number. If this number is 15, if this number is 400, then I go down 400 rows. And then at that row, I have listed two numbers, a limit and a base register. And the limit tells me, and then what I do is I check this tells me where it actually is going to be in memory. When is there an error? If the offset is less than the limit, then everything is good. Remember what the limit is? The limit is the size of the whole thing. So if whatever the base is, I don't care. But the D part is like within the segment. This is the segment number, and this is the offset within the segment. So if within the segment, the D has to be less than whatever the limit is here, because maybe this segment is very small, and the D, I have many, many bits here. So if it's like too big of a number here, then he's going beyond the end of this segment. If the segment limit is only 10, then this number, if it's larger than 10, then I've gone outside the thing. Okay, now if everything is all well and good, then I take that D that I have, which is the offset, and I continue on with it, and I add it to the base register that I've found over here, which is the real location of physical memory. Because I may have, this S is not the real location. This S is what I thought was the real location. I thought the real location was whatever SD is, like 11001111, whatever it is. I thought that was the location, but no, it's not. I'm going to go to the segment table and get a new base, and I'm going to add that base. I'm going to prepend. Really, it's not. This really is not even an add. Oh, is it an add? Yeah, it's an add. I'm going to add that base to the D, and I'm going to get a new number, and that number will be where it actually is in physical location. It's going to push me to a different location. So if I give a numerical example, if S was 5 and D was 5, so S takes me down 5, so I go to row 5, and let's say D is 5, and the limit here is 100. So it's 5 is less than 100, so I go over here. Now the base over here is 200. So I'm going to take 200 plus the D, which is 5, and get 205. And this tells me that I'm in physical location 205. But the original address that I produced was only 55. It was 55 or whatever that means. Maybe it was 10, whatever that means, 55. Because in binary. But whatever. Okay. So in other words, the address that I got here is the logical address. The physical address is whatever the base register plus the offset is. That's the idea of segmenting. Okay, so just a second. So now we're on to paging. Paging is another scheme. Let me get a picture. Let's look at this picture before I talk about paging. Paging is another idea. So we talked about contiguous. We talk about segments. Now I'm jumping into the final way of doing things, which is actually the one we're going to spend the most time on, put it that way. We can say what we're going to do is like this. We're going to take all the memory. This is the physical memory, all the memory of the computer. This is obviously a much smaller picture than the real memory is. Now, the real memory is very large. But let's say, guys, stick with me a few more minutes. Drink something non-alcoholic, and we'll continue. pages. So what we do is we do like this. Take all the, this is a very clever idea. We take all the memory. Remember, the segments were different sizes. Now we're going to say, no, take all the memory and divide it up into equal sized units. We'll call them pages. So in other words, if the memory is, let's say, 100 megabytes, we'll make 1 megabyte size pages. And we'll divide all the memory into 100 pages of each one being 1 megabyte. And they're one after the other, obviously, 0, 1, 2, 3 until 99. Or in this case, we have 8 pages. But you can have 100 pages. You can have, if it's 100 megabyte, if it's 100 megabytes, then, and each one is a megabyte, each page is a megabyte, and we have 100 pages. In this case, let's imagine that these pages are a megabyte. So then this would be memory of only 8 megabytes. So there's 8 pages. All the memory is cut up into these units. Now, when program comes along, Mr. Process comes along, and he says, hi, I'd like 4 megabytes. We say to him, oh, you want 4 megabytes? That's exactly 4 pages. So here's your memory, your logical memory of 4 pages. What you think starts at 0, 1. First one is 0. Last one is 4 megabytes minus 1. Whatever the address of the last byte in your program is. But we are not going to find a contiguous place for you. We are going to spread you around in the computer in any pages that we should so decide. So, for example, your first page will be over here in the physical memory. Your second page, page 1, will be down here. Page 2 will be above it, and page 3 will be all the way at the end. And how are you going to find your pages? Well, very simple. You'll say, I would like page 0. So you'll go to what's called a page table. And you'll look at, if it says page 0, it must be row 0. If I wanted page 1, I'd go to row 1. And each row has exactly one piece of information. Where in the actual physical memory I need to jump to. So this says 1. So if I want if I want some byte on page 0, I'll go to the page table and I will find it. Is in page, I want page 0. I'll find that it's actually supposed to be page 1. So I'll jump over to page 1, and there, lo and behold, I found page 0. If I want page 1, I'll go to my page table, I'll go to row 1, and it'll say 4. And I'll say, oh, that must be page 4. I'll go down to page 4 in the physical memory, and here it is. So every process will have a page table associated with it, which will tell it the real locations for its pages. Now, in such a scenario, I will not have any external fragmentation, because the smallest size that will ever be will also be the biggest size. It'll be exactly 1 page. The holes will always be in 1 page units. And I can always use them. They're never too small to use, because I can have my pages anywhere I want. For every process, he can use any page anywhere, and he always wants a page of the same size. Now, where will there be fragmentation? What if program comes along and says, hi, I don't need 4 megabytes. I need 3.5 megabytes. So how many pages will we give him? How many pages will we give him if he says he wants 3.5 megabytes in my example?
4.
You give him 4. How much internal fragmentation will there be?
Yes.
What? He wants 3.5 megabytes of space. We're going to give him 4 pages. Each page is 1 megabyte. How much internal fragmentation will there be?
Half a page.
Half a page, which is half a megabyte. And how much external fragmentation will there be? Trick question. How much external fragmentation will there be? Remember, for external fragmentation is tiny little holes that I can't use. He came along and said, give me 3.5 megabytes. I gave him 4 pages. The answer is there will be no external fragmentation because because I'll always have the holes will always be the same size and they'll always be usable. And the definition of external fragmentation is that I have holes that are too small to use. These holes are never too small to use. They're all usable. Okay. So that's the paging. Now let me go back. That was to get to the picture. So this sort of says an overview of this in words. Now the physical address space of a process can be non-contiguous. Process allocated physical memory whenever the latter is available. I can give it more. If he needs a new page, another page, he wants to have more space. There's always, I'll be, as long as there's some page somewhere available, I can always give it to him. Avoids external fragmentation. There will be no external fragmentation. The only fragmentation there'll be is internal. Avoids problem of varying size memory chunks. I won't have varying size memory chunks like I had in segments. In segments, for every segment, I needed to know how big was it, its limit. Now I don't need to know that because every segment is essentially the same size. It's one page. So I always know exactly how big it is. The only thing I do need to know is how many pages each program uses. Okay. Divide the physical memory into fixed size block called frames. So we on the one hand, we call this paging. On the other hand, the physical memory, we divide it into frames. Now, the frame size is equal to the page size. The page size and the frame size is it's almost like interchangeable terms. The frames is when we're referring to the physical memory. The page is when referring to the logical memory. The size is always a power of 2. The size of the page is the power of 2. And it's usually between 512 bytes and 16 megabytes. As you're not going to have pages more than 16 megabytes or smaller than a half a megabyte. No, half a kilobyte, right? 512 bytes is a half a kilobyte. That would be very small pages. This would be very large pages. Divide the logical memory into blocks of same size, which we're going to call pages. Remember, he says the logical memory we call pages, so the same size as the frames. You need to keep track of all free frames. Right, all free memory in the actual RAM. To run a program of size n pages, you need to find n free frames and then load the program into those free frames. You need a page table for each process to translate the logical to the actual address. The hard drive could also be split into pages. We will have internal fragmentation, as I explained. So what we're going to do is, how are we going to find the right page? We said we have a page table. We don't have a picture of it here. Here we kind of have a picture of it, yeah. So how are we going to find the page? So remember, an address is produced by the CPU. Or actually, let's stop here. We'll stop here. And we're at the actual computation of paging the pages, of converting regular addresses to page addresses. Important topic, definitely important topic. All right, Shikoyach to everybody.
So much. Have a good night.
Thank you.